Welcome to the P4 workshop of May 2022. My name is Deb Chatterjee. I work for Intel within the Intel Ethernet product group. And today it's my pleasure to give you an in-depth tutorial on a new kind of infrastructure programming development kit that we call IPDK. So let's get started. So today we are going to talk a lot about infrastructure. So maybe it makes sense for us to get into the same page of what we mean by network infrastructure. A generally accepted definition of network infrastructure is that it's the combination of hardware and software that enable network connectivity and communication between users, devices, applications, and the internet itself. A decade ago, when the network infrastructure used to be a lot simpler, it was mainly the vSwitch, storage, and crypto. But today it's a lot more complex. For a very modern data center like Google's, the network infrastructure is a combination of different types of networks, such as the data center network, as well as the software-based public WAN and the private WAN. For Facebook, for instance, the network infrastructure is the backbone that handles both the machine to user traffic between Facebook and internet, as well as the machine to machine traffic within machines inside the Facebook data center. Network infrastructure is growing fast in complexity, performance, and scale. To keep up with the demands on the network infrastructure, we need it to be very highly programmable. And today, I'm going to talk about a new development kit for infrastructure programming that we call Infrastructure Programmer Development Kit, or IPDK. So yes, the last 30 years have been truly transformative. The internet, cloud, and mobility revolutions have transformed the way we live and work. From Google search to Facebook APIs, the distributed design pattern is everywhere from cloud to edge. A deep learning model for an advanced recommendation engine today may use up to 10 trillion parameters. These data sets are so huge that they no longer fit on a single computer, and access patterns rarely have locality of reference. Therefore, scale in this paradigm has meant looking into microservices, but performance remains a challenge. The very low latency needed by today's real-time interactive applications are driving us to the edge. Edge computing is taking off now, and more computation will continue to move to the edge. Most significantly, infrastructure is changing into a software-defined ecosystem, and it needs to stay open and modular so that software can scale and evolve at a fast pace. And since the building blocks of this complex infrastructure fabric is expected to be highly heterogeneous, we need to allow the developers to build once and run everywhere. Therefore, we need an abstraction layer. In the current data center architecture of network infrastructure, the CPU is like the human brain that controls almost all of the hardware and software functionality. All other compute elements, including the NPUs, the GPUs, and other types of purpose-built accelerators, they're all connected to the CPU. This model is simple, and so it is used everywhere, regardless of the size and usage of the data centers. But today, this model is facing challenges. First of all, the cloud service provider or CSP model can monetize the core. So there is a real benefit in freeing up the cores. Even in non-CSP environment, if the CPU is not running infrastructure, it can then run more complex application workloads otherwise. Secondly, the traditional desktop-based application functionality has changed a lot. And in today's web-based applications, often running AI, ML workloads, mission-critical workloads, or other new type of workloads that often need very purpose-built hardware accelerators, these are not found in CPUs. And thirdly, the bare metal hosting model means that the CSP has to vacate all the infrastructure components from the CPU and move them to somewhere else. These three trends resulted in a new class of processors that we within Intel call the Infrastructure Processing Unit, or IPU, and others may call Data Processing Unit, or DPU. The IPU capabilities include presence of their own general purpose processor, such as ARM cores or x86 cores. And this is used for not just running control plane, but also other parts of software that may not have purpose-built hardware acceleration. It needs to have the ability to boot a general purpose OS, such as Linux. It needs domain-specific hardware acceleration capabilities, such as NVMe and RDMA. It needs to have software-defined device functions that are highly programmable. It needs to be able to offload the whole software subsystem, such as the network stack or storage stack, including their control planes. Additional requirements are strict security isolation from the host on the hardware level, and out-of-band management, where the IPU device is managed separately from the server where it resides, or the IPU device can be used to manage the server. To efficiently harness the capabilities of different types of these devices in a complex network infrastructure fabric, we need a powerful development kit that can provide a layer of abstraction. This is why we need IPDK. Infrastructure Programmer Development Kit, or IPDK, is an open source, vendor agnostic framework of drivers and APIs for infrastructure offload and management that can run on a CPU, IPU, DPU, or a switch. IPDK runs in Linux and uses a set of well-established tools such as SPDK, DPDK, and P4 to enable network virtualization, storage virtualization, workload provisioning, root of trust and offload capabilities found in the platform, and other essential components of infrastructure. IPDK provides a common platform for increasing performance, optimizing resources, and securing the infrastructure as a component of the Open Programmable Infrastructure, or OPI. When we try to accelerate the infrastructure part of a new application under IPDK, we use a three-step approach. We first delineate the business logic versus infrastructure. This delineation is necessary because the business logic is the customer's secret sauce. And then we focus on the infrastructure part, and we simplify infrastructure management by using standard interfaces between logical boundaries of the devices. And then finally, we optimize using a compiler-driven target abstraction. This way, the code written once can be maximally reused across different types of infrastructure components, such as CPUs, IPUs, FPGA-based IPUs, or switches, as well as other vendors' DPUs. There are two main families of APIs in IPDK. The first one is called Infrastructure Application Interface, or IAI. IAI is a northbound API for exposing devices and services for workload apps. It exposes the platform capabilities and is usually RPC based. IAI is target agnostic. The other API is the Target Abstraction Interface, or TAI. It exposes the different target capabilities using device functional APIs. So one may say that TAI is essentially a family of APIs. For the different use cases, there may be different types of TAIs. One frequently used TAI is the table-driven interface, or TDI. The TDI is a data model-based API, and anything that has a table-based abstraction fits quite nicely. For our P4 use cases, we mostly use TDI. TDI can be used in non-P4 use cases, as well as other members of the TAI family other than TDI might also emerge in future. Now, of course, for an initiative of such magnitude, we can't enable everything at once. So we have decided our journey is going to be use case driven, with the most common use case first. So what we are focusing on and will be available as the first IPDK release in July 2022 is infrastructure as a service. This includes virtual networking, storage, and crypto offload across virtual machines, containers, and bare metal. Our next target, on which we are already much further along, is platform as a service, which will look into accelerating container networking, Kubernetes, sidecars, Envoy, MongoDB, and other components. We will also look into acceleration of other inline applications such as firewalls, intrusion detection systems, network telemetry, 5G, and wireless infrastructure, and handling infrastructure of complex AI/ML clusters. Let's take a deeper look into one such use case, which is the infrastructure as a service. So within infrastructure as a service, our goal is to retain a common control interface, irrespective of whether we are using virtual machine hosting or bare metal hosting. Same IPDK apps will be used in both cases. These apps, these configuration apps will then in turn talk to the higher level end applications. We'll also use the same common interfaces, or essentially the same semantics, to connect devices to hosts and VMs. Semantics such as create a port or create a disk will remain the same across these two different usages. And finally, with respect to the target abstraction APIs that I talked about previously, we intend to use the same APIs for both the software target or a hardware target, like the Intel IPU. The Intel IPU has unique hardware capabilities to accelerate the hardware offload of infrastructure as a service, such as packet parsing and processing, NVMe offload, RDMA offload, crypto offload, compression offload, and other aspects. So IPDK is a completely open source community driven project. There is a common terminology that we use in conjunction with IPDK, and that's recipes and ingredients. Recipes identify any of the major use cases, and then we delineate, simplify, and optimize for this use case as we had shown before. The ingredients then are the functional areas below a recipe. Today, some of the defined IPDK recipes are network data plane, block storage, microservices, telemetry, inline function, and others. And then under the network data plane recipe, the ingredients could be P4 compiler, P4 SDE, P4 OVS, IPsec, and TLS. So as a new contributor to IPDK, you do not just have the option of working on any of the existing recipes and ingredients. You're also welcome to come and define new recipes and new ingredients. So IPDK is well set with open source development and governance practices. We have support for reviewing and approving new patches, and we have IPDK maintainers in place. For the ease of building IPDK and playing with it, we are releasing everything in the form of Docker files and pre-built containers. The IPDK.io website is up. The code is in GitHub. And for collaboration, we have set up Slack channels. please come and join us. This might be the perfect time to introduce Diamond Bluff, OPI, and what is their relationship with us. So we came up with the IPDK idea through our work on doing hardware offload of infrastructure as a service on multiple Intel platforms. In a similar way and around the same time frame, Red Hat came up with a similar initiative named Diamond Bluff, whose objective was to foster a community-driven, standards-based, open ecosystem for next-generation architectures and frameworks based on DPU, IPU type technologies. So then through multiple discussions, we both agreed that it would be best to combine the two initiatives under a common umbrella, below which both IPDK and Diamond Bluff will continue to be subcomponents. That project is what we call Open Programmable Infrastructure Project, or OPI, and OPI will be moving under Linux Foundation soon. In March 2022, we had the first developers conference event under OPI. It was joined by a number of big industry heavyweights such as Facebook, Dell, Ericsson, F5, and many others. The presentations from them assured us that we are indeed trying to solve a very important problem with IPDK. So I am now going to flip through some of these slides from the OPI conference events pretty rapidly. So Dell told us that without a standard for infrastructure service deployment, it is going to become a game of infrastructure roulette for the data center developer to figure out which among the myriad IPUs and DPUs are going to succeed and what will be their programming model. They insisted we urgently define a multi-vendor open DPU IPU framework. And that's exactly what we are trying to do with IPDK. Lightbits even provided an IPDK shopping list of what features we should provide and emphasized on two main things, simplicity and robustness. From Ericsson, we heard the IPDK requirements from the telco perspective, again emphasizing on multi-vendor DPU, IPU standardization, but Ericsson was also very vocal about the importance of coexisting with today's CPU-centric infrastructure, which is going to change gradually over time. And another presentation from Dell emphasized on the importance of separating out the business logic from the infrastructure, which we are already doing. Marvell told us that they were able to take the IPDK code from the IPDK GitHub and able to run on their ARM-based Octeon processor, which was a big motivation booster from us. So now I am now going to turn to the second part of my tutorial, which is why and how P4 is such an important central piece of our IPDK framework. The first three steps in this slide is usually how infrastructure programming has been done till now. We always start with a cluster of disparate apps with their different data plane requirement. Then we try to bring some uniformity by declaring them in a standard way using C, C++, or P4, or a combination of both. And then that software is further optimized using data plane acceleration methods such as DPDK or eBPF or even machine instructions. With IPDK, we have added one more step and a very important step, which is to leave the details of hardware capabilities or hardware fitting as the last step decided by the compiler. This gives us the opportunity to keep most of the code common, and the compiler backend for the specific targets mostly handle the much smaller amount of target specific code. And this approach is based on our confidence on the growing maturity of the P4 language and tools and its acceptance in the community. Just one look at the number of participating companies under the p4.org forum tells us how wide is the spread of P4. from software companies to ASIC vendors, enterprises, telcos, cloud service providers. Today, P4 is truly everywhere. Both the P4 compiler and the associated tools are quite mature. New architecture specs such as the portable NIC architecture or PNA is getting added. People's experience of using P4 is leading them to suggest new P4 constructs and syntaxes that can become part of the next P4 language standard. And this thriving ecosystem, IPDK is trying to leverage fully from this ecosystem. This is the vision that we had right from the beginning of our work on IPDK, that we should be able to write a single P4 that can then be used on multiple targets by compiling with different P4 compiler backends. A P4 DPDK backend will allow that code to run efficiently on pure software. Mount events backend will permit that code to run on the Mount events IPU. The Tofino compiler backend will port it on the Tofino architecture. And the FPGA backend will make it run with the different FPGA IPUs, such as the Canyon family of products. Well, that was our vision, and the moment of truth has come. Let's see how successful we have been. We are going to run a simple L3 forwarding rules P4 file on multiple targets. And in all the non-Tofino targets, the P4 OVS has been used as the control plane. So now you will see a recorded video of how we run a simple L3 P4 file on the software target. This demo was recorded by Sandeep Nagapattinam from Intel EPG Software.
We are going to look at a simple L3 demo for DPDK target on KVM. Here is a P4 file for this use case. This P4 file has one table, which is our IPv4 host table, and it has one key, which is our IPv4 destination address, and the match type is exact. It has actions send, which would send to a particular port. It also has an action drop, which would drop if the match key has matched. The default action here is a no action. Let us go ahead and create artifacts for this P4 file. So we have downloaded open source P4C compiler, and the executable is built from there. The P4C DPDK executable is used here, and for the target DPDK, and the output files are P4 info file, your BFRT JSON file, context.json, and a spec file. The input for this executable is our P4 file. Let me go ahead and create these artifacts. So this is terminals which I'm going to show today, and the terminal top left is to run OVS, bottom left is to create our P4 artifacts, program pipeline, create ports, and also to program rules. The three terminals here are to run SCAPI to send the traffic. The other two terminals are to run TCP dump and see the traffic is reached to the ports or not. Let me go ahead and create P4 artifacts first. Okay, we use the P4C DPDK compiler. Okay, the artifacts are saved in output directory folder. As the artifacts are created, let me go ahead and start OVS. Along with P4 OVS that we have built, it also generates a build another executable named OVS pipeline builder, which takes a config file as an input and generates a pipeline builder bin. And this pipeline builder bin file is used to program the forwarding pipeline. Let me go ahead and first create the pipeline builder file. Okay. Before that, let us see what is the content of this config file. This config file has a consolidated information of BFRT JSON and the path to context.json and path to the spec file. So the pb.bin, the pipeline builder bin file, will have all the consolidated information of these three files. Yes, it has generated a pb.bin file. Now, let me go ahead and first show the topology that we are going to see for this demo. The topology has two executables. One is p4kettle and GNMI CLI. P4kettle is used to program the pipeline and configure the rules. GNMI CLI is used to create the tapots that we are going to use for today's demo. Here we are going to create 4 tapots. The rules that we are going to program are any packet which matches the destination IP 1.1.1.1 should be sent to port 0, which is tab 0. Any packet matching destination IP 2.2.2.2 should be sent to port 1, which is tab 1. 3.3.3 should be dropped. First, let me go ahead and configure 4 tab ports via GNMI CLI. These tab ports, the moment we create it, it will create a kernel netdev as well. Yes, it has created a kernel netdev. Let me go ahead and configure or create the remaining 3 tab ports. Yes, the CLI successful. Let me bring up my 3 tab ports. Yes, my 3 tab ports are up. Now, as I was mentioning earlier, we need to set the forwarding pipeline and we need a pipeline builder bin file and P4 info. So we use OVS p4kettle to go ahead and program the forwarding pipeline to the target. The pipeline is successfully programmed. Now we can see few logs on OVS side, which would say the pipeline is being programmed. Now, let me go ahead and configure rules. As I was mentioning earlier, the rules are 1.1.1 need to send to port 0, 2.2.2.2 need to send to port 1, which is our tab. Yes, the first rule is successfully configured. You can see the logs. Second rule also is successfully configured. Let me run scapi. We'll try to send packets over scapi and then see if the packets are reached to tab 0, tab 1, respectively. Okay. Now, I'll be sending packet with destination IP as 1.1.1 from tab 2 port, which is also bind to the target, and the number of packets are 2. Let us see if these packets will be reaching on tab 0 or not. Yes. Now, the P4 file rule has matched where the destination IP is 1.1.1. It is sent to port 0, which is a tab 0. Let us try to send 2 packets from the same tab 2, which is binded to the target for destination IP 2.2.2.2. Yes, these 2 packets are received on tab 1. Now, let me go ahead and send a packet which doesn't match to any rule that we have configured. Here, I'm sending a packet with destination IP 2.2.2.3. The packet should not reach to any port. It didn't reach to tab 0 or tab 1. Now, let me go ahead and delete the previously configured rule. I'm going to delete a rule where 2.2.2 was earlier sending to tab port 1. Now I'll delete the rule. So the packet should not be sent to any ports going forward. Yes, the rule is successfully configured again. Let me try to send the packet from scapi to destination IP 2.2.2.2, and it should not be reached on tab 1 or on tab 0. The packet is not reached on tab 1. Now, let me configure the third rule where destination IP is 3.3.3 and the action should be dropped. That means it should not be sent to any of the ports. Yes, this rule is successfully configured. Let me try to send a packet. It didn't reach tab 0 or tab 1. Let me try to see if this packet is reached on any port on the KVM target. It didn't reach on any port. So here I'm filtering with host IP and the incoming packet, which are ours. Thank you.
So now we are going to run the same file on the Tofino target. The demo was recorded by Sayan Bandyopadhyay of Intel XFG, which is the previous barefoot networking team.
Hi. Today we are going to compile a simple program called simple L3.p4 written with PSA architecture. and specifically for Tofino class of switches. So the compilation went through. Now start Tofino model. The switch T process for Tofino. So now shell has come up on the process. We are going to log into the CLI. This used to be called PFRT. We are changing it and modifying it to something called as TDI, table-driven interface. So this is the IPv4 host table. Which the P4 looks like this. It's a match action table with one key field, which is an exact field. It has 3 actions: send, drop, and no action. The default action is drop. Let's add an entry with action send. Let's add another entry. And now we can dump the table, and it shows that the entries have been programmed.
So now we have come to the third demo, which is on the Big Spring Canyon FPGA IPU target. This demo was recorded by Anbuvelu Venkatraman from EPG Software.
Hi, I'm going to show simple L3 demo on BSC IPU. In this demo, the DPTK target is running on SOC. The host whatever net PFs are connected to this DPTK target to the backend whatever net PFs. The DPTK target is programmed with flows to forward between these two whatever net PFs on the host. Okay, let us go to the demo. Okay, here you see the 3 terminals on the left side, which is connected to the host, and the 2 terminals on the right side is connected to SOC. Now, let me run the OVS on SOC. Before running OVS, I have to bind the whatever IPFs on the SOC to IGBYO. Now let me run the OVS. Now let me add the to whatever net PFs to the DPTK target. Ports are added. Now let me load the forwarding pipeline with simple L3 pipeline builder and the P4 info. Now let me program the flows. I'm programming the flows according to this flow. Like whenever the destination IP is matching with 1.1.1, it would forward the packet to the port 0. And similarly, when it is matching with 2.2.2, it would forward to the packet port 1. Now the flows are programmed. Let me send the packet between these two interfaces using SCAPI. And starting the SCAPI first terminal. I'm here pulling the packet using TCP down. I'm pulling both the interface, which is like equivalent to PF1 and PF2. Okay. Now I'm sending the packet to the Ethernet interface 1 from the Ethernet interface 2. Since the destination IP is matched to 1.1.1, so it is forwarding the packet to the Ethernet interface 1. Similarly, I'm sending the packet to the Ethernet interface 2 from the Ethernet interface 1. Okay. Now you see the packets in the ETH2 interface. Okay. Now I'm deleting the flow. That is matching to a destination IP 2.2.2. And again, I'm sending the packet to same destination IP. Now you see the packets are not received anywhere in ETH1 or ETH2. So similarly, I'm going to show the dot packet. Now, no interface should receive the packet. That's all. Thank you.
And finally, we will now be running the same file on the Mount Evans IPU target. This demo was recorded by Nupur Uttarwar of Intel EPG Software.
Hello everyone. Today I'll be demonstrating a simple L2 program on the SmartNIC Mount Evans. Let's take a look at the topology. I have Mount Evans on host 1, which has a physical port P0 connected back-to-back to a foundational NIC CVL, physical port ENS802F0, which has IP address 10.5.5.10. We are using OVS P4 cutter utility to program the rules to be able to send traffic from the APF interface on Mount Evans, hooked up with data plane IDPF driver. To be able to do this, we program the rules using OVS P4 cutter to our FXP pipeline. The first rule is if the destination MAC matches the MAC address of foundational NIC interface, take action as sent to port 0. If the destination MAC matches the MAC address of IDPF interface, this one, take action as sent to vport 17. On Mount Evans, we have reserved the first 16 vport IDs for the physical interface. So the first physical port P0 will have the vport ID as 0. So that's why for any outgoing packet, the first rule says send to port 0. And for any incoming packet to the APF interface will take the first available vport IDs after 16, which is 17. So the action for any incoming packet is send to vport 17. Now let's take a look at the demo. I have color-coded the terminals for better visualization. On top left, I have P4 OVS running on host 1 with Mount Evans. On bottom left, we'll be using this window to monitor the packets using TCP dump. And on top right, we'll be using this window for configuring our pipeline and configuring the rules. And on bottom right, I have the terminal for foundational link interface where the IP address is this, and we'll be using SCAPI to send the packets. Before we go ahead and start the demo, let's take a look at the P4 program. So as part of the P4 program, the apply block says that if the Ethernet header is valid, and if the packet is TX, go ahead and apply a E-forward table, else go ahead and apply a I-forward table. Now let's take a look what the content of this E-forward table are. The key used is a destination MAC address, and the match we are doing is an exact match. If the key matches, then take action as send to port. And for table I-forward, which is for ingress, the key used is again a destination MAC address, and if the key matches, take action as send to V port. So this will hit a small exact match block in the FXP pipeline. I've already created a binary executable using OVS Pipeline Builder and P4C compiler for PNA-MEF. Let me go ahead and set the pipeline. On the left window, you can see that the pipeline is set correctly. Now let's go ahead and program the rules. The first rule is for the TX side. So the destination address will be the MAC address of foundational link interface, and the action is sent to port 0. And the next rule is for RX. So the destination MAC address, which is a key, is the MAC address of your IDPF interface of Mount Evans, and the action is sent to P port 17. Let's go ahead and program both the rules. And on the left window, you will be able to see that the rules are getting programmed correctly on the FXP pipeline. Yeah, so you can see that here. Now let's go ahead and send a packet from foundational link to Mount Evans. I'm using Skippy to send the packet. So as you can see, that we can see the packet on host 1. Let's send one more packet just to be sure. Yeah, you can see both the packets here. Now let's go ahead and delete the rules and see if we are still able to send the packet. Okay. Deleting both the rules which we just programmed. And you can see that the rules are deleted from the pipeline as well. Now let me go ahead and send one packet. Yeah, as you can see, no packet is being received on host 1. So this confirms the RX side. Now let's go ahead and send the packet from Mount Evans to the foundational NIC. Let me start SCP here and TCP dump here. Okay. Before we go ahead and do that, let's just program the TX rule. This should help us to send the packet. And sending the packet to foundational link, and you can see that the packet is received. Just send one more packet. You can see that the packet is received. Yeah, this concludes the demo of simple L2 program on SmartNIC Mount Evans. Thank you.
So now you have seen how we run the same P4 file on multiple IPDK targets. This was our pledge of maintaining the developer's time investment by being able to reuse the same file in other targets. Well, the demo that we saw used a very simple P4 file. In different IPDK projects, we are using much more complex P4 files. So now I will quickly flip through some of them, mostly to show you the power of P4 that lends itself to so many use cases. For instance, this file called linuxnetworking.p4, this is our starting point of the P4 OVS work. This next file is a TCP connection tracking P4 file that is used in conjunction with the Mount Evans IPU's powerful hardware capabilities for connection tracking. We are using this P4 file for a Kubernetes load balancing application. So we are at the end of our journey. I have told you that IPDK is a target and platform agnostic infrastructure programming kit. You now know that IPDK is entirely in open source and in active development. Please come and join us. I have introduced OPI and told you that IPDK is a part of OPI and OPI will shortly move under Linux Foundation. One developers conference for OPI has already taken place in March 2022, and there will be 2 conferences every year going forward. First major IPDK release is 22.07, which is going to be in July of this year. And the next release is going to be 23.01 in January 2023. So we are following the conventions of the SPDK releases, and in this way, we'll be making 2 releases every year, one at the beginning of the year and one at the middle of the year. And I hope I have also been able to explain to you that P4 is a cornerstone of IPDK. We hope to create newer use cases for P4 through IPDK, such as the ones that I briefly flashed. We are also extending P4 support into Linux kernel, on which there is a presentation in this workshop itself. So that's all. If you have questions, please write to me or Dan. Thanks for listening to me, and have a wonderful rest of the day.